In this unit, we're going to be looking at aggregates for concrete. Typically, aggregates make up the largest volume of a concrete mix and typically consist of coarse aggregate and fine aggregate, sometimes referred to as sand. And you can see in this slide that the aggregates vary not only in size but also in shape. Some of it being crushed, some of them being non-crushed. And you can see that we have a pretty good distribution of all sizes. Typically, the coarse aggregates consist of 20 millimeter nominal size here locally in the Winnipeg area, but aggregates can also be larger, can extend up to 56 and 75 millimeters for mass concrete. And you can see that the fine aggregate goes down to as far as the number 200, or in the metric Canadian series, 0.08 millimeters. Okay, here we have fine aggregate or sand. Sand can be natural sand from natural deposits from a pit, or in a quarry. When you're processing aggregate, you can use crushed aggregate and you'll crush it down to the finer sizes. Typically, fine aggregate is aggregate that is identified as being smaller than 5 millimeters, and that is by the Canadian metric sieve size series. If you were looking at the US standard sieve series, then it would be particles smaller than 4.75 millimeters. Typically, sand or the fine aggregate content makes up 35 to 45% by mass of the total aggregate. The coarse aggregate consists of gravel and crushed stone, typically greater than or equal to 5 millimeters. And again, typically in the local area, we're 20 millimeter aggregate. However, between 10 and 40 millimeters is quite common, depending again on what the concrete is going to be used for. You can see from the slide that the left half of the photo shows rounded polished aggregate, and on the right shows crushed stone. Typically, you don't want the polished stone, okay? You won't get the adhesion or the bond as well as you would with the rough crushed stone. In other words, you need good bond between the cement paste and the aggregate. That's what gives you the strength of concrete. It's the bond between the cement paste and the aggregate itself. So, what is the source of aggregates, the coarse aggregates and even the fine aggregates? Well, we know that aggregates consist of minerals and are typically made up of one of the three types of rock types, which you may have studied earlier on. And we know that the three main classifications of rock are igneous, metamorphic, and sedimentary. And obviously, our concrete aggregates consist of one or more of these rock types and minerals. In the next few slides, we'll start looking at minerals and actual rock types that the aggregates are produced from. As you can see here, we've got various minerals, sulfates, iron sulfides, iron oxides. Again, this is just more for interest sakes, and so you have an idea of what some of the type of rocks and minerals that we use in concrete. One of the main ones here, magnetite or hematite, okay, the iron oxide. These are basically metal based, and hematite is a very heavy, dense rock. Its density. It's used a lot in concrete that is going to be used for radiation shielding, something you may encounter in a hospital or in the type of facility that has radioactive materials stored in them. And again, some of the igneous rocks. You're quite familiar with the basalts. The granites are very, very common. A lot of our local aggregates here in the Winnipeg area, we use granite, and we'll also be looking at the sedimentary. Basalt is a very dense rock type of igneous rock and is used frequently in concrete where you want high durability. Sedimentary, more common here to the Winnipeg local area. Again, we have sandstones, clay stones, Siltstones, agrolite, and shale. These are undesirable. Okay, they're very low density. They break down under abrasion quite easily. So again, you wouldn't want them in a concrete that is subjected to abrasion. Okay, so obviously you got to keep an eye out for aggregates. If you're not too sure of your sources, you may want to do petrographic analysis to determine if you have some undesirable rock. Same with chert, very undesirable. These are referred to as low density aggregates, and they do not provide much durability in a concrete mix. Again, the metamorphic rocks, rocks that have undergone change, were previously igneous, they may have been previously sedimentary, or they may have been previously metamorphic rocks that had undergone further alteration. Again, some of the more common ones, the marble, the slates, the schist, okay, these are, and the gneiss, these are rocks that have been previously other rocks, and they may be used in concrete. Not so much here locally, however, maybe in other areas they may be used. Let's look at normal weight aggregate. Aggregates that we use typically for normal weight concrete. Concrete that has typically densities between 2200 and 2400 kilograms per cubic meter. So for the most common aggregates, sand, gravel, crushed stone, again under CSA standard A23.1, we look at our aggregates to ensure that our aggregates meet that specification. Lightweight aggregate, sometimes used for special applications, typically not for our pavements. These are concretes that are made with low density aggregate or lightweight aggregate, shales, clay, slate, and slag. And you can have structural lightweight concrete, typically between 1350 to 1850 kilograms per cubic meter. You do not use these aggregates for normal weight concrete, especially the clays and shales. And again, you can see in the photo on the slide, you have various types of aggregate, the various shales, clays, and even slag. Lightweight aggregates, well, pumice, perlite, vermiculite, which is sometimes used in insulation, and I believe now has been banned. But anyhow, these are aggregates that are very absorptive, they're very lightweight, and a lot of times they're used to produce concrete where you want to have insulating values, maybe a roof slab, not so much structural, but maybe more for insulating. And again, your densities will vary with that concrete between 250 to 1415 kilograms per cubic meter, which you can see is very lightweight compared to normal weight concrete. And then we have our heavyweight aggregates, similar to that hematite I had mentioned earlier. And these are some of the types of aggregates. Iron, steel punchings are shot. Many times iron are used in dry cast hardener, where you maybe do a floor surface, and this floor may be subjected to very heavy steel wheel traffic. So you want to make sure you have a very dense and durable, non-abrasive surface. So you may want to use iron or steel punchings. The magnetites, again, and hematites might be used for shielding. Concrete will be used for radiation shielding. And again, you can see that these densities are pretty high. Typically, our normal weight was 2,300, and we're looking at 6,400 kilograms per cubic meter. So very high density concrete. The next couple of slides lists the aggregate characteristics and corresponding tests to determine those aggregate characteristics. Again, there's numerous tests that we look at for aggregate to make it ideal for concrete. And again, the tests you can see, there are CSA tests, there are ASTM tests, there's even ASTO tests. So there's standards. Typically, these standards are the ones that are specifying the type of tests and the procedures required to produce those tests. So we're looking at some of the characteristics: abrasion and degradation resistance. Very important for pavements subjected to high traffic loads and wear and tear. Abrasion. Freeze-thaw resistance. Extremely important in our climate. Maybe not so much in California or in the southern states. However, for our climate, definitely. Sulfate resistance. Some areas are very high in sulfates, as is Winnipeg. So again, the aggregates can break down due to sulfate attack. We know that particle shape and surface texture has a bearing on the suitability of the aggregate for concrete. It's grading. Do we have a good distribution of sizes? And there's the tests again that are performed, the CSA standards and the ASTM standards. There's also definitions of the mineral types and constituents in the aggregate. Bulk density. What is the density of our aggregate? We use density, and you'll be using that a little later on when we do concrete mix designs. We have to know the density of the coarse aggregate if we are to design a mix based on volume. Relative density and absorption. Again, important. Absorption. How much of the mixing water will this aggregate absorb, take away from our hydration process? So it's important that we know the absorption of our aggregates. Surface moisture, again, a test to determine how much free moisture do we have in our aggregates. As you know, you're going to be adding water to concrete during the batching operation. But some of that water could also be free water sitting on the aggregates in the stockpile. Then we determine compressive and flexural strength. The aggregates contribute greatly to the compressive and flexural strength of the concrete. What are the aggregates made up of? Are the aggregates resistant to alkali reactivity, which has a big bearing on volume change? If the aggregates undergo volume change, so does the concrete. Definitely, we may have cracking. In the previous slides, we looked at some of the tests that are performed to determine the characteristics of the aggregates. So now these tests, typically performed in the laboratory, are going to be submitted from the field, from a quarry or a pit where the aggregates are being processed. So in other words, the laboratory tests are going to be carried out again in accordance with CSA standards or ASTM. These tests have to follow a certain procedure to make sure they're valid. And laboratory tests are carried out on samples of the aggregates submitted. So in other words, are these aggregates representative of the aggregates in the pit? In other words, these samples, were they taken in such a way or such a procedure to ensure that they are representative? Sampling is equally as important as is the lab testing. If the aggregates aren't sampled properly, they are misleading. So in other words, the aggregates may be rejected from use in concrete. The main sample typically is made up of portions taken out of different points in the stockpile. And then again, these individual incremental samples are mixed to ensure that we have one composite sample representative of the total material in the pit. As noted in the earlier slide, the field sample has to be representative of the material being tested. So that includes a minimum sample size should be submitted. The size is dependent on the nominal maximum aggregate. Here locally in Winnipeg, where we're using 20 millimeter concrete aggregate for the pavements, you can see from this chart that the minimum mass of field sample should be 25 kgs. It can be more, but this is the minimum, and that minimum is basically made up of composite samples, individual samples taken in the field and blended to form one composite sample, and that minimum sample should be 25 kgs. One of the more common tests determined on concrete aggregate is to determine its gradation. In other words, What is the grain size distribution? Do we have a good range from small to large sizes? And again, we would test the coarse aggregate for its gradation as we would the fine aggregate. And as you noted last year in Natalie's lab, you guys did aggregate gradations. For concrete, we're looking at using CSA standards. Typically, last year you were looking at ASTM. However, for concrete, in Canada, CSA A23.1 and A23.2 is followed as far as concrete aggregates or concrete materials. And the fine aggregate usually consists of a minimum of about 8 standard sieves and ranging anywhere from 10 millimeters to 0.08 millimeters. So in other words, we want to have from about 3/8 to number 200. Coarse aggregate, you're looking at about 5 to 7 sieves, typically from 20 millimeters, 25 millimeters, down to 4.75. You will include the 1.25 in there, which is the number 8, to ensure that we have a percent passing the 5 millimeter. So in other words, these numbers of sieves that you use is not set in stone. You want to make sure that you have enough so you can get a fairly good grain size distribution of all sizes. Once again, we see the same slide that shows the range of particles for concrete aggregate, ranging from the coarse sizes all the way down to the fine sands, and obviously some of the minus 0.080 or passing 200. When we refer to the grading of concrete aggregate, whether it's coarse aggregate or fine aggregate, we use the term maximum size and also nominal maximum size of aggregate. There is a difference. Maximum size is exactly as the term states, maximum size. In other words, what is the largest size of aggregate? So the maximum size, we would look at the smallest sieve that 100% of that aggregate would pass through. So in other words, if we have maximum size of 25 millimeters, that means 100% of that aggregate would be smaller than 25 millimeters. Nominal maximum size refers to the sieve that would be immediately smaller than the smallest sieve through which all the aggregate must pass. In other words, if we're looking at 20 millimeter nominal size of aggregate, 100% of that aggregate must pass the 25 millimeter, and 100% may pass the 20 millimeter. However, typically you can have some oversize. So in other words, you can have grading limits for 20 millimeter sieve as 90 to 100, which would mean then that you're allowed 10% oversize. In other words, 100% of the sample may not pass 20 millimeter. It may, and that's okay. Okay, so there's the two differences. And make sure you're aware of these definitions because they do come up on quizzes and they do come up on final exams. So in other words, you have to know the difference. What is maximum size and what is referred to as nominal maximum size. So why is it important to know the gradation and maximum size of aggregates that we use in concrete? Well, it is important in the fact that it affects the concrete mix in numerous ways. So that is one of the key elements, is to look at the gradation, know the gradation of the aggregates that we're proposing to use. In other words, it's going to affect the amount of aggregates we use in a mix design. And later on, when we're designing a concrete mix, you will see how the maximum the maximum aggregate size and the grading, how it's going to affect the amount of aggregates that we use. It'll affect the amount of cement and water we need in our mix. Obviously, the workability. How well can we work with that concrete mix? The aggregates have a direct bearing on it. Can we pump the concrete? In other words, we're going to design a concrete mix if we know we're going to place it with a pump. Again, gradation and the size of the aggregates are important in coming up with a good pump mix. Economy. Obviously, money always comes into play. Porosity. How porous is the mix? Okay, are we going to have a good dense mix with small voids or hardly any voids? Shrinkage. We know that anything that changes state from a fluid, concrete is initially hydraulic when we first mix it, and then as it sets up and cures, it becomes a solid. So anything that dries usually shrinks. Okay, volume change. The grading of the aggregate has a very big bearing on how much is it going to shrink. The finer the grading, the more the concrete's going to shrink. For a simple reason, the finer the aggregate, the more water we need to make it work. So again, we'll look at that when we're doing concrete mix designs. Durability. The aggregates have to be well graded to provide a good durable mix that would be resistant to abrasion. And strength. Okay, concrete with coarse aggregate in proportion to fine aggregates is going to have a direct bearing on the strength. And obviously, we have to look at uniformity between batches. When we're batching concrete, we want to make sure that each load delivered to the job site is consistent. So in other words, we have to know the grading of the aggregates, and we have to make sure that that grading is consistent so we can produce a good, consistent concrete mix. This slide is more for your own interest sakes. It basically relates to the maximum nominal size of aggregates and to the design of forms that may have reinforcing steel in it, more for a structural application. And it gives you an idea of how aggregate size pertains to the size of forms. Last year, you will recall in your Geotechnical Materials 1 lab, you were performing sieve analysis typically on base materials, A base, C base, may have been drainable materials, drainable base materials. For here, we're looking at fine concrete aggregate grading limits. This slide shows two grading limits for FA1 and FA2. The difference being that FA2 are grading limits that are a lot coarser than for FA1. You can have aggregates, fine aggregates for concrete that may be coarser than some other applications, depending again on what your mix is for. If, for example, we look at one of the sieve sizes, let's look at the 2.5 millimeter sieve. For FA1, you can have up to 100% passing the 2.5 millimeter. And looking at FA2, you can see that you're going to have anywhere from 40 to 25% oversize. So it's a lot coarser. And typically for our pavements that we'll be looking at for City of Winnipeg, we look at fine aggregate to meet FA1. The previous slide were grading limits for fine concrete aggregate. This slide shows two typical size ranges. CSA has various size ranges for a coarse concrete aggregate. In this slide, we can see that there's a size range of 20 millimeter to 5 millimeter and 14 millimeter to 5 millimeter. Those are the ranges of the aggregates. And you can see that grading limits change. Some of them are coarser, some of them are finer. Obviously, if we're looking at the 14 to 5 millimeter, you can see that the grading of that material is a lot finer than when we're looking at 20 to 5 millimeter. For our City of Winnipeg pavements, we're going with the 20 to 5 millimeter, and we'll be looking at that when we're doing a concrete mix design. Again, for both grading limits, you can see that the aggregate has to be clean, 0 to 1% passing the 80 micrometer or the number 200. We want to make sure that we don't have fine deleterious materials, whether they be the clays or silts. They're going to hinder bond. They're going to hinder the development of strength. So aggregates for concrete typically have to be clean. The cleaner, the better. This slide shows the graphical representation of the grading limits for the coarse concrete aggregate, the 20 to 5 millimeter size range, and for the fine concrete aggregate, 10 millimeter down to 0.08 millimeters. This is an Excel. You may be using that last year. You may have just plotted them manually on a grain size distribution form that was presented to you in your lab. In an earlier slide, we looked at some of the effects that the grading of concrete aggregate has on the concrete mix characteristics. You will recall we looked at porosity. In other words, how many voids, the size of voids. This slide shows a little graphical representation of volume of voids based on aggregate grading. If you look at the two beakers, the aggregates are different in size, but each one is uniform. So in other words, we have in beaker number 1, coarse aggregate, uniform in size. In the middle beaker, we have finer aggregate, but each particle is also uniform in size with one another. So the volume of voids would be consistent. You can see by the level of water in the slides that they're level. In other words, you have the same volume of voids. However, if you take aggregate that is well graded, it consists of coarse aggregates, medium-sized aggregates, fine aggregates. In other words, it has a good distribution of all sizes. The smaller particles filling in the voids between the larger particles. Thereby, the voids are reduced. If you put water into the beaker, you would have a lot less water. So you can see that the liquid level in the graduates represents the voids. The amount of cement paste that you will need for concrete is related directly to the void content of the combined aggregates, not just the coarse aggregates and not just the fine aggregates. It's the total aggregates, the combined grading between the coarse and the fine aggregates. This slide illustrates the dispersion of aggregates. If you had aggregates only, no cement paste, you can see from the upper sketch that the large aggregates by themselves will be in contact with another, with voids in between. If we use cement, we have a cement paste, as represented by the lower sketch, we have a good matrix. The amount of paste is greater than the void content, so it separates the aggregates and will provide workability. The actual amount is influenced by the cohesiveness of the paste and the workability. The paste, which consists of water, supplementary cementing materials, your cements, and the real fine aggregate, creates a matrix around each aggregate. You want each aggregate to be coated with a cement paste, and you want the cement paste to be bonded well to each individual aggregate. That's what gives you your strength. When you test concrete in a lab and you look at a specimen that was tested, say in compression, and you split it apart, and you see each aggregate split or sheared, that is a good indication that you have good strength concrete. You do not want the aggregates to pull out from the cement paste. In other words, the cohesion between the aggregate and the paste, you do not want that to let go. You want that bond or that cohesion to be greater than the tensile strength of the aggregates. You want the aggregates to shear. An important characteristic of fine aggregate is its fineness modulus. You will be looking at fineness modulus when we're doing concrete mix designs. We need to know how coarse that fine aggregate is when we're designing a concrete mix. It will dictate how much coarse aggregate we need. So what is the fineness modulus? It's an index of the fineness of the aggregate. How fine is the grading? The higher the FM number, the coarser the aggregate. FM is a good control for aggregate processing. The FM of any shipment of aggregate, when you're producing aggregate, say in a quarry or in a pit, should not vary by more than plus or minus 0.2 from the initially approved value. You will come up with a grading of fine aggregate that you use in your concrete mix design. Quality control testing of that fine aggregate as you're producing it should not vary. It's a way of ensuring that the grading is consistent. You can have different aggregate gradings. However, they may have the same FM. We'll look at that a little later on when we're doing mix designs. How do we determine it? It's determined from your sieve analysis. The FM is obtained by adding the cumulative percentages by mass retained on each of a specified series of sieves, and you divide that by 100. If you recall from your sieve analysis, just before you calculate percent passing, you may have been instructed to determine the cumulative percent retained. You don't need the cumulative percent retained to calculate the percent passing. However, you do need it when you're calculating the fineness modulus. And that is one of the reasons why we have it on our sieve analysis data sheet. You don't need it, but we've got it there because when you're doing concrete mix designs, it's imperative that we determine the fineness modulus. The number 200 sieve or the 0.08 millimeter sieve, we do not use that in calculating the FM. It's just from the larger sieve down to the 100, the number 100. And here we can see an example of calculating the FM. We have a typical sieve analysis data sheet, and you can see that we have the individual percent retained, we have the cumulative percent retained, and then we have the percent passing. So it's the cumulative percent retained column that we use, and it's a summation of those values. So you can see starting at the 10 millimeter sieve going down to the 0.160 or the number 100, we do a summation and we just go down the column and we add 0 plus 2 plus 15 plus 35 plus 55 plus 79 plus 97, and we get a total of 283. You can see we did not include the 0.08. Then we take that total and we divide it by 100. And now you can see we have an FM modulus, fineness modulus, of 2.83. This is a good example to show you how to calculate it. Every time you're involved in testing fine aggregate, gradations of fine aggregate, get in the habit of calculating the FM. It gives you a good indication for the consistency of your grading from one sample to the other. And you will see later on that CSA has an FM limit from 2.3 to 3.1. In other words, the FM should fall in between 2.3 and 3.1. The amount of water and cement or cementitious material requirements is influenced by the maximum size of aggregate. If we look at this graph, you can see whether we're looking at non-air entrained concrete or air entrained concrete. The graph indicates that as the maximum nominal size of aggregate increases, the water demand decreases. The larger the aggregate, the less water required. If we need less water and we're maintaining a water cement ratio, the resulting amount of cement will also decrease. So we can see how aggregate size influences the amount of cement and water required. And you can see that the relationship is the same for air and train versus non-air and train. Another interesting fact shown by this graph is that air and train concrete requires less water than non-air and train concrete at a given maximum aggregate size. So if we look at the 19 millimeter aggregate size and we go up, we can see that the amount of water required for air and train concrete would be less than non-air and train concrete. Earlier on, you will recall we looked at various physical characteristics of aggregates and the ideal characteristics that are required for concrete. One of them was the abrasion resistance, and this is especially important when concrete is used in roads or floor surfaces that are subjected to frequent and heavy traffic loads. And to determine the abrasion resistance, there's a test referred to as the Los Angeles abrasion test. Essentially, steel balls are thrown into a drum that can revolve. The aggregate is also thrown in with these steel balls, and after 500 revolutions or 1,000 revolutions, depending on the size of aggregates that you're testing, the aggregates are tested again to determine how much of the aggregates have abraded. In other words, how much have they worn down. The procedures I will not quiz you on. Just be aware of what test is used to determine the abrasion resistance. Another important physical characteristics that we look at for aggregates is referred to as soundness. Soundness, it's the ability of aggregates to resist volume changes that are due to environmental effects, freezing and thawing, alternate wetting and drying, temperature changes, all can affect the volume of the aggregates and its changes. Aggregates are said to be unsound when the volume changes induced by those environmental factors results in the concrete deteriorating. Some of the deteriorations can be local scaling. You've seen that, how the surface just peels off. Extensive surface cracking, disintegration over a considerable depth. In other words, the scaling, sometimes referred to as spalling, also goes down in depth. So we know then that the soundness of the aggregates has a big bearing on the concrete itself. This slide summarizes the test procedures. Again, read it for your own interest. I do not quiz you on it. However, know that the soundness of aggregates is important and what causes aggregates to be unsound. Again, just read this slide for your own interest's sake. In accordance with CSA, there are soundness limits that the aggregates must meet. And you can see for fine aggregate using magnesium sulfate solution, the fine aggregate shall have a maximum loss of 16%, and the coarse aggregate a maximum loss of 12%. And that's when it's determined in accordance with CSA standard 823.1. Not only does gradation influence the physical performance of a concrete mix, but particle shape and the surface texture of that aggregate is equally as important. Various particle shapes are available in aggregates. We know that some aggregates can be rounded, as shown in the photo here. Typically, water deposited materials or like river gravels. So the corners, the edges have been worn off. We have irregularly shaped aggregates where some of these particles are somewhat worn off, but not totally. So we do have some rounded edges, some angular edges. Angular, as you can see in the photo, sharp corners shows very little evidence of wear. And typically when we produce aggregates from a quarry, we'll have about 100% crushed aggregate. So all the edges will be sharp and angular. Some deposits, the aggregate may be flaky or flat, as you can see in the photo, and typical of rocks that are laminated. We consider it flat when the aggregate's ratio of width to thickness exceeds 3, 4, or 5. So in other words, there's a dimensional ratio between the edges. Elongated, when the length to width, the ratio exceeds 3, 4, or 5. So flat is width to thickness, elongation is length to width. And again, if we refer to clause 4.2.3.4.3 of the CSA standard A23.1, it covers the specifications for aggregates, elongation, and flatness. Again, we can see some photos here where we have a flat rock, elongated. You can see the length to width, angular, sharp edges, and round, where it's cubical, but it's round in shape. In other words, the three dimensions can be considered close to one another in size. So how do the various particle shapes perform in a concrete mix? Well, if we look at the rounded aggregates, typically these are the most suitable in concrete, okay, and used quite widely. Flaky and elongated particles, they actually reduce workability. So if that's the case, we have to increase the water demand. And when we increase the water demand, we're going to reduce the strength. Angular particles do give better bond due to the interlocking. So in other words, there is better bond between the cement paste and the aggregates, and the rough texture gives better adhesion. However, when you have angular particles, sharp edges, peaks and valleys in the aggregate, you're going to have an increase in surface area. With an increase in surface area, you are going to require more water to maintain the workability. So if we look at this concept where if we keep the cement content the same and the same workability, we will get better strengths with rounded aggregates than we will with angular because we will be using less water. And for pavements, the strengths in most pavements are not that considerably high, whereas we cannot make good strength concrete with rounded aggregates. Just to summarize surface texture and strength, we can see that surface texture is not a very important property from a compressive strength point of view, okay, for structural applications. But aggregates with a rough surface texture does perform better under flexural and tensile stresses. And for pavements, the pavements are in flexure. So from that point of view, one would think, well, we should always use rough textured, sharp, angular, crushed aggregates for pavements. Well, if we do, we're going to have problems with workability. We increase water, we have to increase cement. From an economical point of view, the mix is more costly. As I said earlier, the strengths for pavements are not that high that we cannot make good strength concrete using rounded aggregates. That way we will keep the cement content and water content proportional, so we will have a more economical mix. So surface texture, although important, from our point of view for pavements, we can get by with good rounded cubical aggregates. that are clean. We've been discussing water demand for concrete based on the aggregates, whether they're sharp and angular or whether they're rounded, and how they will influence the amount of water that will be needed for the mix. Moisture conditions of the aggregate are very important. The absorption and also the surface moisture of the aggregates have to be determined so that the total water content of the concrete can be controlled and correct batch quantities determined when we're batching concrete. The internal structure of an aggregate particle is made up of solid matter and voids that may or may not contain water. If we look at the four moisture conditions, we can have aggregate that is oven dry, which means there is no moisture present whatsoever, strictly dry aggregate. We have air dry, we have saturated surface dry, and we have wet. Aggregates that are in the oven dry or air dry state and in the SSD state have absorbed water. When aggregates are in the wet state, they have absorbed water, plus they have free water on the surface. So you can see in this sketch where the absorption is and where the surface moisture occurs. Oven dry, okay? The absorbed water, the surface water, free water is all driven off. You have a constant mass. You only have the inert aggregate itself. Air dry, no surface moisture present. However, you will have some moisture present in the inside. In other words, the pores will be filled. Saturated surface dry, SSD, just as the name states. No free moisture on the surface. However, the voids are filled with aggregate. So they're saturated from an internal point of view, but no water on the surface. And when the aggregates are wet, they're saturated and they have free or additional water on the surface. And this additional water has to be taken into account as part of the mixing water when you're batching concrete. The absorption characteristics of the aggregates will influence the amount of water that must be added to the mix, and that amount of water is required to hydrate with the cement. We can now summarize the total moisture content of the aggregates in the various states. If you have oven dry, there's no moisture. Total moisture content is 0. Air dry, moisture content is less than the potential for absorption. In the saturated surface dry state, the total moisture is equal to the potential absorption. And in the damp or wet state, we now have water content that's greater than the amount that can be absorbed. The moisture state and absorption capacity of an aggregate is very important when it comes to mix design. Typically, mix design calculations are based on aggregates in the SSD condition. That way, the amount of water that is added to the mix is free water, and it will combine with the cement to cause the hydration process. If the aggregates were in a state other than SSD, we have to make corrections. If the aggregates are less than the absorption, that means that water that we add to the mix will be absorbed into the aggregates and will change our water cement ratio. It will not be used in the hydration process. If the aggregates have surface moisture or free water on the surface, we will then need to reduce some of the mixing water for the simple reason that the aggregates are contributing the mixing water to the mix. Not only does porosity and absorption of the aggregates influence the amount of water required for the mix, it has effects in different ways. It can affect the bond between the aggregate and the cement paste, the resistance to freezing and thawing of the concrete, its chemical stability, its resistance to abrasion, the specific gravity, and the yield or the volume of the concrete for a given mass of aggregate. In our last slide, we noted that the amount of moisture in aggregate can influence or result in an increase in the volume or the yield, typically contributed by the sand, and it's a phenomenon known as bulking. Bulking is the increase in total volume of moist, fine aggregate over the same mass dry. Surface tension in the moisture holds the particles apart, causing an increase in volume. If we look at this slide, we can see three gradings. We have a coarse graded sand, sand that's medium grading, and fine grading. If we look at the horizontal scale, we see that if we have dry aggregate, dry rotted fine aggregate, and we increase the moisture content, we know that with an increase in moisture content, for each type of grading, whether it be coarse, medium grading, or fine grading, we have an increase in the volume of the aggregate compared to its dry mass. So you can see at 0% moisture, if we add 0% moisture, at all three types of grading, the volume is virtually the same. As we increase the moisture content, the volume of the aggregates increase. So in other words, this is going to influence the yield of our mix. And at a certain moisture content, if we keep adding it, the actual volume starts to decrease, regardless of whether the aggregate is a coarser grading or has a finer grading. You can see that these are almost very similar to a Proctor curve. Looking at this slide, we can see that if the bulking increases by volume, there is a relationship between the bulk density, whereas the bulk density decreases. So we can see as the bulking increases to a maximum, the bulk density decreases. And then as the increase in moisture content continues and the bulking decreases, the bulk density of the aggregates increase. The next several slides show how aggregates influence the performance of concrete. We know that we have good aggregates. We also know we have aggregates that aren't so good, and it can cause a lot of stresses. One of the phenomena is known as decracking, which is cracking of pavement, and it's caused by the freeze-thaw deterioration of the aggregates. And here you can see a slide where you can see the aggregate on the right being cracked. In other words, the moisture content of the aggregate and its porosity is such that it's causing it to crack. And that obviously distresses the pavement. And typically, it occurs at transverse joints and longitudinal joints running parallel to it. So it's a function of the pore properties of certain types of aggregate particles. And in Winnipeg and Manitoba, we used to have this problem way back in the late 60s and early 70s. Back then, we were using aggregate maximum sizes of 40 millimeter. And since then, when this distress was noted, studies were done and they determined that if we reduce the maximum size of aggregate, the porosity and the rate of absorption changes, and we can reduce decracking quite a bit. I don't think we ever totally eliminated it. However, we have reduced it. And you can see that they run parallel. The cracking of the pavement, you'll notice, has a pattern where it runs parallel to the transverse and longitudinal joints. And then with time, it extends outward towards the center of the slab. So closely spaced cracks form parallel to transverse and longitudinal joints. Another distress of pavements that can be caused by the type of aggregates is pop-outs. You can see in this slide that a crater-like depression is formed when the surface pops out. And typically when you look at it, you can see that there's an aggregate particle in the bottom of that crater. Typically, this is caused by low-density aggregates that have high absorptive rates. And when they have high absorptive rates, they take on moisture quicker and they'll expand. And we can define that as a breaking away of a small fragment of concrete surface due to internal pressure within the aggregate particle. Some of the low-density aggregates we looked at were shales and cherts, and those are aggregates that are not suitable for concrete. In our local deposits here in Winnipeg and the Interlake, we don't seem to have this type of aggregate. However, southwestern Manitoba, you have to be careful because there are some low-density shales and cherts that can cause problems. If you look at this type of distress on a pavement, and this can actually happen on asphalt pavement also, can you imagine having this on a runway where you have jet engines? They would suck up this debris off the surface if this was occurring, and it can be catastrophic. Damage can occur to the engines, and even fatalities can occur. So this is one type of material to look for, and be very cognizant of the fact that it can cause some severe problems. This slide will show various types of aggregates and how they contribute to the amount of shrinkage the concrete can undergo. And if we look at some of these aggregates here, we can look from sandstone to slate to granite to limestone to quartz. And on the left-hand side, the scale shows drying shrinkage after 1 year. And you can see that sandstone has the highest shrinkage and quartz would be the lower. So obviously, the type of aggregates that we use, we want to make sure that shrinkage is minimized. And we have to select aggregates that do have good properties and very low shrinkage properties.